So we had started section 3.3 last time. We had taken a look at a lot of different things about subtraction, and we had finished looking at the algorithms that we have. And we have a few problems left that involve other bases, and that's where we're picking up. Okay, so other bases. So we're doing just a couple of random ones. There's nothing special about the base 8 or the base 3 that we're doing our examples for. But we want to recall that we've talked about in these bases. So base 8 has digits 0 through 7. And we're going to do subtraction in base 8. And this is going to look like what happened when we did the other base addition, was what we did it for in the other section, where I'm going to show you a couple of ways that you can do the problem so that you kind of have a handle on how to do it. I'm pretty sure most of these don't ask you like for a specific method, but that way you've got a couple of examples if there is a specific one requested. All right, so this one is 3, 4 base 8 minus 1, 7 base 8. And I'm going to start with the standard algorithm. And these are base 8, but I'm not going to write them because it'll kind of cloudy up my picture of what's going on. We just need to remember it as we work. So 3, 4 base 8 means I can't do 4 minus 7. So there's not enough. So I have to regroup. So I take one of the 3s, or I take one of the 8s. So I take away one from the 3. So there's 2 left. And that means I have taken away 8, right? Because everything in that column is in groups of 8. So it's like I have 3 groups of 8. I take one of the groups of 8. There's only 2 groups of 8 left. Okay? That 8 will then be combined with the 4. And 8 and 4 is the number 12 if you're counting individual units. That's not that shouldn't be a cause for consternation. 8 plus 4 is 12.
I don't understand.
8 plus 4 is 12.
Because you're not regrouping the 10, because usually when you regroup it's 10. So you just add.
So you take the number here, 4, and you add the base you're in. Normally our base is base 10, so we add 10 to it to get 14, but we're in base 8, so we're adding 8. That's how we're ending up with 12. Is that okay?
Yes.
We're counting them individually, right? So that we have 12 of them, 12 individual objects. Because we want 12 of those individual objects so that we can remove, how many of them? 7. So if I have 12 individual little like blocks, right? Think about our concrete model, 12 individual blocks, and I remove 7 of them, how many of them are left? There are 5 left. And if I have 2 groups of 8, because that's what this column represents, and I remove 1 group of 8, how many groups of 8 do I have left? 1 group of 8. So I have a 1 and a 5, and this is base 8. I think you'll like the equal additions for this one, probably a little bit better. So I have 3, 4 minus 1, 7. So if you remember, we did equal additions last time, but it was very much at the end, and we did it really fast. Equal additions has the property, or the goal is a better word, a goal of no borrowing. So we don't want to regroup anything. And the way that we go about doing that is trying to find the value that would be closest to become a 0, like the value on bottom, to make it a 0. So in particular, this 7 on the bottom is really close to becoming a 0. What do I need to add to the 7 to become a 0 in that space holder? 3 if it were base 10, but we're in base 8.
1.
So we have 1. I need 8 items to group together to make a long. Okay, so I'm grouping things together in 8s. So if you want to think about, also you can think about your list of numbers. We did this before too, that after the 7 is the 1, 0, 1, 1, right? All the way up to 1, 7. After 1, 7 is 2, 0. Okay, so we need 1 more added in order for this to become a 2, 0. And the goal is zeros, really, for the purpose of no regrouping or no borrowing. But with equal additions, if there's 2 things and I'm trying to find the difference between them, if I add 1 here, I have to add 1 here. So I'm moving them both. I'm shifting them both by the same amount. So if I add 1 to 3, 4, what do I get? 35, exactly. And at this point, because I don't have any more regrouping that I would need to do, I would be done and I'd be able to subtract. So what is 3, 5 minus 2, 0? 1, 5. Base 8. Okay, let's do another one. This one's in base 3. So remember the digits are 0, 1, 2, and then it starts repeating. So after this, we would have 1, 0, 1, 1, 1, 2, and then 2, 0, and we would keep going. Okay? So we'll do the standard algorithm first, 1, 0, 0, 2, and we're subtracting 1, 1, 0. Yes, ma'am?
So in the last one, we can just pick which one we want to do?
Unless it tells you a specific method. Yeah. On this one, I'm going to do the standard algorithm, but then I'm also going to do, I think I'm going to do expanded algorithm on this one to show you just another algorithm and what it would look like. So that if you're asked for it specifically, you have another example, but also if you just like it better, you can choose it.
So that second one we did was the equal additions?
Yep, that's equal additions. Mm-hmm. And the first one was standard. And on this one, we're going to do standard first, just like we did in the last one. And then we will do expanded. All right, so standard algorithm. When I don't have to do any regrouping, it's really nice, right? Like the very first, the ones column, 2 minus 0 is 2, no problem. The next columns, though, have problems because I can't actually do the subtraction because it's 0 minus 1 in each of them. So just like in our system, we're trying to regroup. So we have to regroup all the way until I have something to regroup from. So I'm going to have to go all the way over to the fourth digit. That's the ones column, where there's a 1 in that column. So this 1 will have to go down by 1. But I'm in base 3. So when it goes down by 1 and 1, it's going to borrow 3 into the other column. So I've added 3 here. And that'll be fine, except that I have to do it twice because I have another column that still needs something. So I do this one more time. This 3 has to go down 1, and I regroup a 3 over here. Okay, just like in our system, we borrow 10s because we're in base 10. Here, we're borrowing 3s because we're in base 3. At this point, we're able to subtract. 3 minus 1 is 2, and then 2 minus 1 is 1. And this is base 3. Please remember, and I've mentioned it before, but please remember if you have a base other than 10, you must write it. The assumption is you're in base 10 if there's no written bound value beside it. Okay? So let's look at what this looks like in expanded algorithms. So in expanded algorithms, we actually write each of the values out by the place value that it is. So we write down 1 times, and normally we write 1 times 1,000, but we don't have the thousands place. We have the 3 squareds place. Is that right? 3 cubed. 3 cubes place. We'll start there. We have 0 in the 3 squareds place. We have 0 in the 3's place, or 3 to the 1 if you prefer. And then we have a 2 in the 1's place. That's what expanded looks like in base 3. And we're subtracting from that 1 in the 3 squareds place, and 1 in the 3's place, and 0 in the 1's place. So what we see happening here on the far right, again, is just this number 2 showing up. That's perfectly fine. But it can't do the subtraction. And I've written addition. Let me make it clear that I'm doing subtraction by putting the minuses in between these, actually. I'm subtracting each of these pieces. So I've got 0 3's minus 1 3. Well, I can't do that. I can't take 0 and take 1 away. So I'm going to come all the way over here to where I have something that I can take away from. So I'm taking 1 away from here. And when I do that, I actually have 3 squareds now. Because what is 3 times 3 squared? Don't overthink this. What is 3 times 3 squared? No? We'll do properties of exponents later, but do you remember? Those of you at Prop and Stat should remember something. I'm looking at the two of you. You add exponents. It's 3 cubed. Right? 3 to the 1, 3 squared is 3 cubed. Do you see the 3 cubed that we took it away from? Right there. That was 3 cubed. We took it over to the next column and we separated a 3 away from the 3 squared. That's what's happening. So there's 3 squareds that we moved. And then we can move it one more time because I need one more of them over there. So this 3 will become a 2, and I'm going to move one of those over here, so there's 3 left over here. Then I have my 3 minus my 1, and I have my 2 minus my 1, so it's 1, 3 squared, plus 2 3s, plus 2 1s. So I end up with 1, 2, 2, base 3. Okay. This one works really nicely to do with equal additions too, right? If I wanted this to be equal additions, I've already got part of the way there. There's a 0 here already, right? I don't have to do anything for it. But the 1 in the second column right here, I'd have to add 2 to it, right? So a 2, 0, because it's in the second column, so I'd add a 2, 0. Add a 2, 0 on bottom and 2, 0 on top. I would add another 2 right here, right, if I needed to, right? I'd keep adding numbers until I ended up with no need to regroup. And that's what it would look like for equal additions, much like I've done the problem before. So there's different varieties of ways that we can think about this. The last thing we're going to do in this section is mental math. We talked about mental math in section 3.2. Mental math means math you should be able to do in your head, and we are going to stick with how many steps? 3. 3 or fewer steps. So if it's taking you more than 3 steps, there is some other approach that you should be considering instead, okay? Because for mental math, we don't want too much to be stored at one time. That's not realistic. That said, you're going to write it down because otherwise I can't see what's happening in your head, all right? So the first one we've actually seen before, but we saw it from a different perspective, from addition perspective. This is breaking up and bridging. So breaking up and bridging means that we're breaking things apart. In particular, we're going to break apart the second value into its place values. Notice we're back into base 10 items, so we can breathe a sigh of relief on that, right? So we're breaking the 38 up into 30 and 8. And what we do then is that we take our 46, the original number, and we just subtract 30 first. So what is 46 minus 30? 16. And then we subtract our 8, in this case, second. And what's 16 minus 8? 8. So I guess you could say we did 3 steps if you count the breaking apart 38 to be 30 and 8. I'm not really sure you have to count that one. We did 2 mathematical steps, truly, right? Operational steps. One operation was subtracting the 30, and the second operation was subtracting the 8. So this is breaking up and bridging, okay? The next one is trading off, and we saw this happen before with addition too. Trading off really is just another name for equal additions. The kicker is that when the values are small enough, we can do it mentally, right? So let me flip back real quick to the equal additions we saw last time. This one was equal additions we saw last time. The numbers were a little bit bigger, right? They were 3-digit numbers, which makes it a little more difficult to do in mental math. But when we're doing this with 2-digit numbers, it's not too bad to do with mental math. So here's how this works. I have 46 minus 38, and always, as is the case with the ones we've seen before, we're wanting to get that 38 to be something with zeros. So what do I have to add to 38 to turn the ones digit into a 0? 2. So I add 2 to each of the values. 46 is 48, or becomes 48. 38 becomes 40. So that was 2 steps. I had to add the number 2 to each of my individual values to start with, right? And then I have to subtract. That's step 3. So 48 minus 40 would be my 8 again. Do you see the 3 steps? Okay. Again, could you potentially do those 3 steps in your head? If the numbers are 2-digit numbers, you probably could. Okay. Much bigger than that? Probably not. Yeah? Okay. The last one is an interesting one. It's called dropping the zeros. So this is a really good example of one. Well, and reality is all of these are examples of places where you can't just haphazardly use one. They've got to be intentional for the values you're given. This example is intentionally done here. It's done here because it has zeros on the end, right? If you didn't have zeros on the end, dropping the zeros wouldn't even make any sense. You with me? So what does dropping the zeros mean? Well, it literally means that we ignore the zeros that are at the end, the matching pairs of zeros, And we simply do 46 minus 34. What's 46 minus 34? 12. And then we put the zeros back on the end. I don't really have to worry with the zeros. They're gonna stay 0, right? So I just worry with the values that are not 0. Okay, everybody good? All right.